Okay, so welcome everyone to this week's virtual Rencontres. It's a great pleasure to have Rob Myers from Perimeter with us today, and he's going to demystify all this business with quantum extremal islands for us. Thanks.
Okay, thank you. And thank you for the invitation to come visit you, at least virtually. Maybe in a year or so, we'll be able to do this in person again. In any event, here's my title, Quantum Extremal Islands Made Easy. I have to acknowledge that I've been working with some really smart people, Vincent Chen, Dominic Nunenfeld, Juan Hernandez, Shanming Rowan, all here at Perimeter. Josh Sandor has moved on to Stanford, and Ignacio Reyes, you may know him as a postdoc at AEI in Potsdam, and there's some papers here. In any event, if any of you have seen me give a talk in the past decade, perhaps, you know this is one of my favorite slides, holographic entanglement entropy. What Ruin Takinagi showed us is that we can take a difficult problem of evaluating entanglement entropy in the boundary conformal field theory and turn it into a much less difficult, perhaps still challenging geometric problem in the bulk of the ADS space-time. And holographic entanglement entropy has really drawn a lot of attention because it's become a forum for a bulk, what I call a bulk boundary dialogue. And with dialogue, I mean that the information's really been flowing in both directions. We've learned new lessons about quantum field theory, but we've also learned new lessons about quantum gravity. And so what I'm going to be talking about today are new lessons that we're learning about the black hole information paradox. So just to set the stage then, I should talk a little bit about what is the black hole information paradox. Here I have a Penrose diagram for a black hole, albeit an evaporating black hole. So we can start on an early time slice well, this is Hawking's thought experiment. We start at an early time slice in a pure quantum state. There may be excitations in the space-time here that converge to collapse and form a black hole. But when we take into account the quantum fluctuations, the black hole starts to leak and we see radiation emerging out near the boundary, out near infinity. This, of course, is carrying away energy, and so the black hole becomes smaller and smaller, and eventually the black hole disappears. All of the energy is in the Hawking radiation out here at infinity. Now, the puzzle is that the calculations show that this radiation is essentially thermal radiation. And so this state on the late time slice is then a mixed state. And so that's a conflict or a tension with the basic tenets of quantum theory, and that we're evolving from a pure state to a mixed state, which is in contradiction with unitary time evolution. Now, we'd like to, or I would like to translate this to a problem involving entropy. And so Don Page showed us how to do that, or talked about that. Here, what I'm showing is the entropy of the Hawking radiation. And so it starts down here at 0 when there is no radiation. But then as time evolves, more and more radiation comes out. And so the entropy goes up. And eventually it stops going up, of course, because the black hole has disappeared and we just have this shell of radiation expanding out into empty space-time. And so that is our contradiction. We started from the pure state, 0 entropy, and we ended in the mixed state with some non-vanishing entropy. Now, what Don argued is that if it is a unitary process, he didn't present arguments that it should be a unitary process, but he said, if it is, then this must be entangled with something, and it must be in particular entangled with what it left behind, namely the black hole. And so at a certain stage in the process, the black hole entropy will come to dominate or bound the amount of entropy that can be in the radiation. And so in these later stages here, the entropy should actually be decreasing and eventually fall to 0. And so implicitly what that's saying is new or hidden correlations between the radiation that was emitted at early times and the radiation that's being emitted at late times, and that would allow or must be what allows for the ultimate entropy of the radiation to go back to zero, i.e. we go back to a pure state. Now, the surprise is, of course, or most of you must know, is that now about 2 years ago, it seems that new calculations allow us to compute this page curve in a controlled manner. And so this was really kicked off by these first two papers back in the May of 2019. But I've also added the contributions of another seminal paper by our friends in Princeton in August of that year. Of course, since then, there's been a whole slew of papers, and this is just a partial list. And I apologize if someone in the audience, their name doesn't appear here, but I could probably fill many slides worth of names if I consider all the papers. If I think about, or if we look at what came out of this third paper, it was a very succinct prescription for how we should evaluate the entropy of the radiation. And it's given the name, or they gave it the name, the island rule. And so in particular, though, they're looking at a system where I have a black hole, namely a gravitational system, and it's coupled to a reservoir, a non-gravitational system. And what they do, or what we want to do, is we want to collect the Hawking radiation. We want to extract it from the gravitating region and put it in the reservoir where we just have, basically flat space physics, and we can manipulate that radiation in the ways that we usually do in quantum field theory. And what the island rule says is that the correct evaluation of the entropy of the Hawking radiation is given by this following expression. And so here what we're doing is we're not just evaluating the entanglement entropy of the radiation in the reservoir, but we're also including the possibility of evaluating the entanglement entropy of the radiation in that reservoir, but also we're testing the possibility in this equation that we include various island regions or various regions in the gravitating part of the space-time. And if we include such an island, then we also include a geometric factor, namely the Bekenstein-Hawking entropy associated with the boundaries of that region. And then by summing these two together, what we do is we try out all the different possible islands. We look for the extremal, we extremize this function. And if there's more than one saddle point, we choose the minimum one. And that is their prescription that they argue gives the correct entanglement entropy of the radiation. And so just as a cartoon or a sketch of how that might work, or how that might reproduce the page curve, we can think about the evaporating black hole. And what you find is in these early stages, you can do this test, you can try out all sorts of different islands, but none of them gives you an extremal point, or none of them gives you a minimal extremum of this functional. And so the answer is that the island is the empty set, i.e. there is no island. And so all we end up doing is the standard, quantum field theory calculations of the entanglement entropy of the radiation sitting in the reservoir. But that's precisely Hawking's calculation. And so we get, in the early stages, this rising part of the curve here. However, if we go to late stages, we've built up a large amount of entanglement between the radiation and quanta that are sitting behind the horizon or in the black hole. And so what one finds, or what one might find, is that there's a new saddle point here with a non-trivial contribution coming from an island. And in fact, that allows for this possibility that the entropy starts to decrease, and it gives you the second half, or the desired second half of the page curve. Now that's just a sketch. but I'll take questions. Sure, go ahead, Joseph.
No, I had a question. You are saying that, there's some information which, some quanta which are sitting behind the black hole horizon.
Yeah.
How can you sit there? It takes you just a crossing time and you're in the singularity and gone. So how can anything sit there?
Okay, well, okay, I did not mean the word sit. I meant that there are quanta behind the horizon, and that by choosing a region beyond the singularity, that you can find an extremum of this functional.
But these quanta fall in the black hole very fast. I mean, they fall in a crossing time, they are gone, right?
Yeah, yeah.
So how comes they can be counted? I mean, if in a sense, we have a process which is supposed to take like, mega zillions of years, and, somehow this quanta, even if for like, 1 second before they hit the singularity and they vanish, they can help me, but, after that, they cannot help me anymore. So.
Well, okay, so I think what you're saying is I haven't given you a very good insight or intuition for what this rule is doing. I haven't given you any details. And I hope, well, I will show you some pictures, some calculations that we've been doing. And maybe what I'll ask you is if you're to hold on, indulge me, hold on to that question.
Sure, no problem. No, I was just confused. I mean, when you said they're sitting behind the horizon, that was the only thing.
But can I ask a sort of more historic question? We kind of knew this 30, 40 years ago, in the sense of there are states behind the horizon whose entanglement with the stuff in the Hawking radiation will purify the Hawking radiation.
Yeah.
So this is sort of encapsulating something that we kind of knew 40 years ago.
It certainly makes use of that. Yeah, it's saying, what you're saying is that by including, or what I'm saying and you're saying is by including these quanta behind the horizon, this number gets much smaller.
Yeah, but isn't that therefore moving the goalposts in the sense that you've just redefined the notion of what is the entropy of the Hawking radiation, because you've redefined it to include stuff that's inside the black hole? And that's
no, you're pointing out to something else, which I was going to point out in about, I don't know, 5 slides, which is, this is a really weird equation.
It's not only that. I'm objecting to the fact that you've moved the goalposts. The original goalpost was to calculate the entropy of the Hawking radiation, but now you're calculating the entropy of a system, which is the Hawking radiation, coupled to some island inside the black hole, which was not the original problem.
I'm going to say it in a different way, but I'm making the same objection. This is a weird equation. I've got a calculation of the entanglement entropy of the radiation that I'm calling the correct, I put it here in brackets, the correct calculation of the entanglement entropy is we do our usual calculations, but I don't just include these quanta into my reservoir. I'm including some other gravitational regions. How does that make any sense? Why is there an entanglement entropy of radiation here and an entanglement entropy of radiation and other stuff on the other side of the equation? And so again, I'm going to ask you to indulge me, and hopefully we'll see how this makes sense. I try and address that very specifically at, I don't know, towards the end of the talk.
Okay, but my point.
I'm going to disagree. I don't think we've moved the goalpost. I think this is what we wanted, and that's what we're getting.
Okay, the right-hand side is is the answer you want, and then you've defined it to be the entropy on the left-hand side. So this is a wish fulfillment statement.
No, I disagree with that. I agree that at this stage in the talk, this is a weird equation.
I'll shut up.
And I haven't. Yeah, I will. I promise I'll try and get to that one. Oh, wow. Okay.
Rob, could I also just add a comment to what Nick was just saying? And again, I just want to add what I was going to ask you later, but since the question has come up, I mean, all the papers I read, and I tried to work through quite a few papers in this field, it does seem to me a little bit of it looks exactly like what Nick was saying. In fact, what you have at the end is that you are back to the remnant scenario. The quanta which are inside remain inside. You redefine the entanglement of what you want to call the entanglement entropy outside to include the inside. So by definition, it comes down. And then where people stop, and where I think the answer has to be found, is that when you look at the quanta outside, they say, no, this is the correct way to think about entropy, the new one that you are going to say. But are you going to address the basic question that if I have quanta in the asymptotically flat region, I can do experiments to ambiguously define what their entanglement means. And if you define it in some other way, it just doesn't do the job. It conflicts with what you see in the lab. So I was going to ask you this later, but I just want to put it out there in case you're going to address it during your talk, but we'll come back to it in the end if that's fine with you.
I think the model that I'm going to present to you actually addresses that, and but we'll see. Yeah,
thank you.
I have to ask for your patience.
Thank you.
Okay, I better move along. So
I
here
mean,
we have
just
this
a question, Rob. Can I just quickly ask
sure.
does the island always lie behind the horizon, or can it extend outside? Or
no, it doesn't always lie behind the horizon.
Okay.
Yeah. And that'll be a point that comes up later as well. I wanted to mention a couple of the key ingredients in these early calculations. Perhaps not needed for this audience, but I'll say them anyway. You know, most of these or in fact, all of those three papers address this question in the context of the ADS CFT. But one of the things they did to change the problem is they added absorbing or transparent boundary conditions, because we had this process where I wanted to extract the radiation and bring it into a non-gravitating reservoir. And so they accomplished that by changing the usual rules of the game of ADS CFT and allowing for stuff to be extracted from the ADS bulk, or in other words, they're coupling the CFT to some external system. Many of the early papers focused on two-dimensional, special two-dimensional kind of gravity called JT gravity. And they also didn't use particularly this geometric formula of Ryu and Takanagi, but rather use the idea of quantum extremal surfaces. And so I'll just very briefly mention these last two. So JT gravity, or Jaquet-Teitelbaum gravity, in two dimensions, the Einstein-Hilbert term is just a topological term. And so what happens is we introduce an extra scalar field, the dilaton, in front of the Einstein-Hilbert term, and that gives us a non-trivial theory of gravity. And this appears in different contexts, but the most exciting one recently has been, it seems to be the dual to a particularly simple quantum mechanical model known as the SYK or Sachdevier-Kitaev model. And I won't say any more about that. One comment here is, though, that I'm not just going to be considering, or when they've been considering, or when they do a calculation in JT gravity, they're not just considering the gravity, but they actually have matter fields running around in the background. And so in our context, or in the most interesting context, this is actually a CFT, a two-dimensional CFT that lives in the background geometry that's controlled by the JT gravity. Now, in JT gravity, we might think about what do the black holes really look like, because if I look at the dilaton equation of motion, it's just R equals 2 lambda. Namely, the Ricci scalar is a constant, but that completely defines the Riemann tensor, or the curvature. And in fact, the black hole geometry is locally everywhere, at least, just an ADS2. And so a typical coordinate or black hole that's written down is a geometry like this. We can see that this blackening factor vanishes at some particular radius, but this geometry is really just the ADS2 geometry. And so this is more like Rindler coordinates, or in the context of ADS, you might call them ADS Rindler coordinates. Of course, in this theory, there's also the dilaton, which has some non-trivial profile in this background. But the horizon, I'm just pointing out that the horizon, or the black hole, is more like an acceleration horizon or a Rindler horizon. Now, we wanted to think about entanglement entropy in this problem. For the RT prescription, what we're doing is we're really extremizing the geometric factor associated with the well, what sits in front of the Einstein term. So there's no area in 2 dimensions, but there is this non-trivial dilaton over 4G that we're extremizing. What's an interesting entanglement entropy question that I can ask in the first place, because my dual theory is a quantum mechanical or a 0 + 1 dimensional theory. I can't have disconnected or neighboring regions of the spatial slice. But in the black hole, in fact, of course, I have 2 boundaries. And so I can ask, what's the entanglement entropy between one boundary and another? And in that context, if I ask, say, what's the entanglement entropy of the degrees of freedom here on this boundary at this time slice, I would extremize this quantity and I'd find that I just evaluate the dilaton on the bifurcation surface or on the intersection of the past and future horizons here. Now, what the new prescription, or what was used in these new calculations, though, is the idea of quantum extremal surfaces. And this is something that was first introduced in the context of trying to understand quantum corrections to entanglement entropy, bulk quantum corrections to entanglement entropy. And so there, what one does is one extremizes not just this geometric factor, but what you add to it is the entanglement entropy of the matter fields that are running around in the space-time, in particular, the entanglement entropy of the matter state on some Cauchy slice that extends from your candidate extremal surface out to the boundary region on the asymptotic boundary. And what I'm indicating in this picture here is that I can choose different time slices or spatial slices to run from my extreme or my candidate extremal surface out to the boundary region. And that won't make a difference because of the unitarity, the quantum contribution or the matter contribution to the entanglement entropy will be the same on these 2 partial Cauchy slices. And so what you really have to do to extremize this quantity is you have to move around the boundary. And that's really the only thing that will extremize well, the sum of these 2. It's not moving around the Cauchy slice. In any event, that's just a well, lightning review of a couple of the ingredients of these calculations. I want to briefly describe an example, but it's not going to be an example of an evaporating black hole. Rather, I'm going to look at a black hole in thermal equilibrium. And this was first done again by our friends in Princeton, but a very similar observations were made by these folks out at UBC. And so there, I'm working with the same system of JT gravity coupled to a conformal field theory. But what they want to do is they want to prepare the system in a thermal equilibrium. And so on the gravity side, we're preparing the Hartle-Hawking state. And so we know how to do that. We work with this 2-dimensional Euclidean black hole, the saddle of the Euclidean path integral, to couple it to the bath. Well, in the bath, thermal states given by, again, a periodic Euclidean path integral. These 2 geometries have the same period, or the circumferences are matched here. And what that's indicating is just that the temperature of the bath and the temperature of the black hole have been matched so that I can have a thermal equilibrium. Now that's a Euclidean instanton, perhaps. How do I get the state? Well, what I do is I take this geometry and I slice it in half along this dotted line here. And then what I've done is I've prepared with this Euclidean path integral in the reservoir and in the gravitational system a particular state on, we can call it the Hartle-Hawking state on this dashed line. And so I can take that picture, the half, and I can squash it down on my page. I get this simpler picture with semicircles here, but that's really just a cartoon of what I showed you on the last slide. I can take that state and I can think about evolving it forward in Lorentzian time. In the gravitating region, what I get? Well, I just get my ADS2 black hole with the horizon here. And in the non-gravitating region, well, it's just flat space. And so I get a flat space region, now one for both sides of the black hole. I can also think of taking that state and evolving it forward or backwards in time. And in other words, I could just think about the Lorentzian manifold. Perhaps that's easier, but the idea is that I've created a very special state on this t=0 slice in the middle of the geometry. Now, a question might be, well, I have a thermal equilibrium here. There's not going to be an information paradox. Why is he showing me this as an example? Well, in fact, if I think about it on the microscopic scale, even though I have a thermal equilibrium and say the temperature and the energy density here isn't changing, this region is continuously exchanging quanta with the neighboring gravitational region. And so we might have an example like this, where I have these two red quanta, which were prepared in an entangled way by that path integral. This quanta just wanders off into the flat space, and so it just remains in the reservoir forever. This one falls into the gravitating region, and then may fall behind the horizon. And so it's stuck in the gravitating region. And so in that process, I'm building up entanglement between the black hole or the gravitating region and the reservoirs on either side. Similarly, it can go the other way. I can start with quanta in the gravitating region. This one falls into the black hole. This one climbs out into the reservoir and wanders off into the flat space. Again, building up entanglement between those two regions.
So, Rob,
yeah,
question.
Go ahead. Sure.
Can you show the slide again?
Yeah.
So in this two-dimensional case, what happens behind the horizon? There's no singularity, right?
No, there's no singularity. I mean, this geometry is ADS space everywhere. Again, what makes the gravity interesting is the dilaton field. And so the dilaton, well, there's this part of the diagram, this vertical line or nearly vertical line from the tips of the diamonds here on either boundary of the ADS. And what you'll find is that the dilaton is actually diverging there. And so you can interpret that as a singularity. One of the things it was on the slide, I didn't mention, but you can find this by dimensionally, or you can find JT gravity by dimensionally reducing near extremal charged black holes in higher dimensions.
Yes.
And so the singularity structure then of those black holes is precisely what I said. You have you have sort of a horizon, there'd be another horizon which forms a diamond up here, and then the singularity would be a time-like singularity on either side that's sort of a vertical line extending from the tip of the diamond upward.
I see. Thanks.
Okay. So what would the page curve look like for this system of an eternal black hole or a thermal equilibrium? Well, if I just took into account this exchange of the quanta between the two systems, that causes the entropy to rise. But in fact, if I did the standard calculation, I would just see that entropy continue to rise, in fact, forever, because the system just sits there in equilibrium for an infinite amount of time. However, if we think the black hole is really of it as a quantum mechanical system that can only store a finite amount of information, then in some sense, the registers of that system get filled at a certain point. And when you do further exchanging, you're actually recycling quanta that actually came from the bath originally. And so what you would expect is that the entropy saturates at a certain point, and it simply remains constant when you're in this recycling phase. And so that's what these authors in this first paper did with this particular system. They applied the island rule. They found that in the early stages, the island was the empty set, or there was no island, and you reproduced the growth phase that the semi-classical calculation would have given us. But then they found that at late times, an island appears, or there was a contribution from this region near the black hole. And in fact, the entropy saturated and remained constant at that point. And so this is actually my first picture with a quantum extremal island, the namesake in the title. It's this, there are two extremal surfaces, one on either side of the black hole, and the island is referred to as a spatial slice extending between those two. And as Andrea noted, in this particular example, in the evaporating cases that people had seen previously, the quantum extremal surfaces were actually inside the horizon. But in this case, the quantum extremal surfaces were outside the horizon. So the island actually extended beyond the black hole. So that's an example in a little more detail, but it might raise a lot of questions. You know, how important is 2 dimensions? You know, how important is JT gravity? You know, there are questions like, where's the Hawking, how's the information really encoded in the Hawking radiation? There were Nick's questions or my questioning about, you know, what is this, how does this really make sense where I'm doing an entanglement entropy calculation on this side that's different than what I'm doing here, but I'm somehow calling that the right answer. And so there's a lot of questions, or as many questions as answers in these early papers. And what I'm going to try and argue or show to you in the next half hour is that, you know, many of these insights can actually be understood in the more familiar context of holographic entanglement entropy. And so that's not to take away from any of this new progress, but it's just framing it in a different setting where we may have some intuition and perhaps even make further progress in understanding things like, well, the details of the page curve.
Can I ask a stupid question, just paraphrasing what I see? We know that the left-hand wedge can purify the right-hand wedge. And so, but at the early stages of the evolution, the left hand, you know, the amount of quanta in the left hand wedge coming out are very, very small, and so therefore you don't see the island. The island is a sort of like a large n. When the number of quanta that have gone, you know, come out of the black hole become large in some n, then you expect holographically there could be some geometric feature that turns up. So the island is simply, I think, a geometric realization of the purification stuff that's in the left hand wedge in this picture. Correct?
I like a lot of those words. I got stuck with left hand and right hand wedge, and that I'm not sure which wedges are.
Well, okay, what I mean is that.
But Nick, yeah. What I'm going to do is I'm going to ask you to indulge me. I'll sure. Just say yes, that's right, Nick, and I'll keep moving along because I can tell I'm not going to get as far as I'd like. But no, I don't want to stop questions. Keep poking away. But I think I haven't even gotten to the interesting part, or what I think is the interesting part of the story. So what I want to do is I want to rephrase this in a context where perhaps it'll seem more intuitive or more familiar. So to do that, the first thing I have to do, though, is I have to remind you about something that people were excited about 20 years ago, namely Randall-Sundrum gravity, or in the context I'm going to look at it, it's actually often called Karch-Randall gravity. And I should say, you know, while this has been the focus of the 3 papers I had, you know, Andreas and his student Hao actually also, well, they did something, well, with the same framework, but it's somewhat complementary to what we talked about. So the idea in Randall-Sundrum is I take some bulk gravity with a negative cosmological constant, and I couple it to a brane, but I let the brane back react on the geometry. This is a finite tension brane. And as a result, what they showed us is that this creates, or that in the back reacted geometry, there's an extra graviton mode that's localized on the vicinity of the brain. Now, a side comment here is that in our papers, we actually allowed for the possibility that there's actually an intrinsic gravitational term on the brain. And I'll just say, you can go look at the paper if you're interested in that. It just gives you another knob to play with in the system. So focus on this ordinary brain, ADS gravity. If you integrate things out, what you find is and I'll say more about the geometry in a moment, but you get an induced gravity theory on the brain. You can see here there's an effective Newton's constant that depends on the bulk Newton's constant, the bulk ADS scale. If I look in the action, the first term is just a cosmological constant term. That depends on various parameters in the bulk theory. And here you can see G Newton in the bulk and the tension. And so this has to do with the back reaction. And then there's an Einstein term. And then in fact, there's a whole series of higher curvature terms in this action. Now, one thing I'm going to do in our context is make one fine tuning where this quantity in brackets is small. And what that means is that the cosmological constant on the brain is much smaller than the cosmological constant in the bulk, or alternatively, the curvature scale on the brain is much larger than the curvature scale in the bulk. And one of the things that buys us is that all of these higher curvature terms are actually going to be suppressed by the ratio of these scales. And so in this regime, essentially what I'm doing is I'm studying Einstein gravity on the brain theory. That's what, well, that's the lesson from Randall-Sundrum. Now, what is this geometry? Or in other words, how do I determine the position of the brain? Well, one approach is I use the Israel junction conditions. And so my cartoon here is just a cross section or a time slice of ADS in D+1 dimensions. What I've done with this metric, though, is I've foliated that geometry with slices that are themselves ADS, but in one lower dimension. Then what I'm going to do is I'm going to chop off the geometry at some large value of rho here. Then I make a second copy and I paste them together. So locally, everything looks like ADS, but there's a jump in the extrinsic curvature across this green line, which manifests the presence of the brain. And so what Werner Israel taught us is the jump in the extrinsic curvature is given by the tension of the brain in this formula here. Now, what was a surprise to me, although it's just an indication of the consistency of this system that Randall-Sundrum gave us, is the other thing we can do is we can solve the gravitational equations of motion here. And what you get is that this L effective is equal to some series involving the curvature on the brain. In this geometry, that curvature is given by this simple formula. And so by understanding this equation here, I can determine what the rho should be, where I should put this cut, where I should put the brain. But and again, that was a surprise to me, well, when we first did this, but it's just indicating the consistency of this standard bulk description and this effective Randall-Sundrum gravity prescription. So, well, okay, this is a warning, just, you know, this already is a cartoon, but what it's indicating is there's a lot of extra space-time here in the vicinity of the green line or in the vicinity of the brain. I'm going to be drawing cartoons like this, where I just take a disk and I draw a green line across it. But the warning here is that there's lots of extra geometry that's hidden in the vicinity of that green line. So that's just a warning along the road. The amazing thing now is that we have not just two descriptions of the theory, but we have three. You know, there's this standard bulk description that I described about putting a brain in and using the Israel junction conditions. That has a holographic dual where there's a boundary CFT that's associated with that gravity system, but there's also a conformal defect now that in my picture runs around the equator of this sphere, but that's the place where the brain reaches out to infinity in the ADS space. But an alternative description of the system is that in some sense, what I can do is take the dual of the conformal defect while keeping the holographic CFT on the asymptotic boundary. Alternatively, you can think about it as integrating out bulk degrees of freedom. And that what that does is it leaves an effective gravity theory on the brain. That is coupled to the asymptotic boundary theory. And so that sets up in this particular framework the kind of system that I want to talk about. What I have is a gravitating system, namely the brain, described roughly by Einstein gravity. It also happens to be coupled to, well, because of the details, 2 copies of the boundary theory. But because that intersects out at infinity, it's also coupled to a separate non-gravitating region, which I describe as the holographic CFT living on the asymptotic boundary of the ADS space. And it's really in this context then that I'll be talking about the information paradox, black holes, and islands. But we'll see what the connection is. In fact, most of my calculations are done in this bulk picture. And so I'll have to be able to translate between these 2 descriptions.
Sorry, Rob, sorry.
Yeah, okay,
but
sure.
Why should integrating out the bulk give anything like local gravity on this brain? I mean, that's a high inferential leap, it seems to me, no?
Well, that's the lesson that Randall-Sundrum taught us here. That's really...
My worry, you see, is your brain, as you draw it on the left, goes very close to the conformal boundary, which you chop off. Now, if you were to integrate, what was chopped off, then I understand that's an ultraviolet region, so you integrate it out. But that's not what you are doing, right? Because, as you point out, the full geometry is the 2 together. So you are integrating out infrared stuff, and
yeah, okay. So there's well, that's a good excuse. There's one set of words that I forgot here. But what you might think, if forget about the green line. Often what we think is all of this bulk stuff is equivalent to a CFT living on the black circle.
Right.
Over here, if I just look at 1/2, well, I've got a lot of the bulk stuff. And so that's, equivalent to, or you might think that that's equivalent to a CFT living on this part of, or this black semicircle. I didn't go all the way out to infinity here, but rather I stopped at some finite radius. And so that might help with the words that, well, you would think that the bulk then induces or is equivalent, the bulk with a cutoff is equivalent to a CFT living on the green line, but with a UV cutoff. Now, the extra thing, though, that Randall-Sundrum taught us is that there is actually an extra mode in the graviton that is localized in the vicinity of the green line. And so it's not just the CFT there, but it's a CFT coupled to gravity. But sorry, go ahead.
Yeah, I know the words, but somehow the UV cutoff you are referring to, I think, has nothing to do with the brain. It's a UV cutoff in the sense of holographic renormalization. Here, you have, by the way, a massive mode on the brain coupled to the whole bulk gravity, and now you want to somehow remove the bulk gravity and only think about I mean, maybe it makes
No.
sense. It's not clear to me at all. No?
Well, I'll try one more time, but are you, here you're used, or you're not unhappy to say that, I can trade the bulk gravity for the boundary CFT.
Yeah, that's what we usually do. Yeah.
And if and the truth is that we never go out all the way to infinity. There should be a little dotted line there, and there's some cutoff. And so really what we do is we do calculations with a cutoff in the bulk, and we say that that's a CFT, and there's some UV cutoff in that CFT. But in the usual ADS CFT, most of the things that we calculate, we can take that cutoff to infinity, and we focus on things that are UV finite. And so I'm using all that same language here, but then you added the words that, except that, well, it's really, this mode is an extra mode localized on the brain, and it's coupled to the bulk gravity. But what you also told me is, or what you also accepted here, is I can trade that bulk gravity for a CFT with a UV cutoff. And so the brain theory is, another way of describing it is, there's this extra graviton mode coupled to the boundary CFT with a UV cutoff.
Yeah.
I agree that all of that is just words. Yeah, okay. All of that is just words.
I remain skeptical, but this doesn't mean, you should
okay.
go on.
The one thing I can point on, well, I didn't do the calculation for you, but the one thing that I can point to that is an actual calculation is the consistency of these two pictures here. And if you go to, I think it's the first of our papers, you can see in detail how this calculation, which is the gravity calculation, matches with this bulk calculation. And so that's one indication of the consistency of that. But okay, you're going to indulge me, and I'll carry on. I want to talk about black holes in thermal equilibrium, but first I'm just going to think about ADS, and I'm going to forget about the brains. This is just empty ADS, and what I want to do is I want to remind you that that can be written in a set of coordinates where it looks like a hyperbolic black hole. Of course, this is none other than the ADS Rindler coordinates. And so this is a coordinate system on empty ADS space, but it's it's constructed in a way that there's an apparent horizon here at this place called rho equals L. And that's these two orange disks in the picture over here. What is that describing? Well, it's really describing the boundary theory, the boundary CFT in a thermofield double state. You might notice that the gauge theory directions, I've got time, but here I've got some hyperbolic geometry. And so this is the boundary CFT on this particular geometry in a thermofield double state, but it's at a very particular temperature, where the temperature is related to the curvature of this hyperbolic geometry here. And this R cross, a hyperplane in D-1, or that's really Euclidean ADS D-1. The Penrose diagram looks like this diamond here, and that's just these two diamonds that are wrapping the boundary in between the two orange disks, or in between the horizons at rho equals L. Okay, we wanted to introduce branes into the picture, so all I'm going to do is I'm going to take a brane and I'm going to run it through the middle of this picture. And what that describes, again, is a thermofield double state, the same boundary geometry, the same temperature, but now I've got a conformal defect in the boundary theory as well. And so I depicted that in my Penrose diagram as this green line running down the center of this diamond. And I'll note that the geometry there is time cross, again, a hyperbolic geometry, but one less dimensions. Another comment is that the geometry on the brane is really inherited from the bulk geometry. And so what you see there is, again, a hyperbolic black hole, or ADS Rindler coordinates. The only thing that changes really is the curvature scale of the geometry. Here, L denotes the bulk ADS curvature scale. This LB denotes the curvature scale in the brane. That was the brain. So if I deconstruct this, or I think about this, what I called the brain perspective, or this middle picture, what I've got then is an ADS brain with some ADS Rindler coordinates given here, and then I've got these two geometries, boundary geometries, that are given by time cross some hyperbolic geometry. And so the brain perspective really looks like this. I've got a gravitating brain with a set of horizons on it. And then I've got the boundary geometries with this particular, with this particular structure here. And of course, the green is gravitating, the boundary is non-gravitating. And so that looks very much like this two-dimensional system that we had before, where I talked about the page curve for a thermal equilibrium system. It's just that the details here, this was actually half of flat space attached on here, and this was half flat space attached on the other. I had sort of ADS Rindler coordinates defining a horizon in the bulk. That's almost identical here, except the flat space actually turns into this hyperbolic geometry across time. And the other thing is that you can see by this fold here is that the intersection of the gravitating region and the non-gravitating region is really a defect in the middle of the space-time. It's not that I chopped off the space-time and glued it on to or chopped off the boundary, the Bass space, and then glued it on as I did in this picture here for the 2 dimensions. And so some of the details are different, but this is really then the setup, or a very similar setup that we had before in higher dimensions. So we can talk about the equilibrium evolution and the page curve in this context of higher dimensional gravity. And how am I going to do that? Well, I'm going to attack it again using holographic entanglement entropy, but let's think about the entanglement entropy question that I'll ask. I've got 2 copies of this on either boundary. I'm going to ask for the entanglement entropy of the radiation or the stuff away from the gravitating region. And so I take a small step away from the defect on either side, and then I ask for the entanglement entropy of the blue region. And I do that twice. So it's the blue region, not just in one of the boundaries, but for both of the boundaries at the same time. I might ask how that geometry evolves in time. Well, the usual time evolution in this picture is more or less the same as if it was a Minkowski-Penrose diagram. And so a constant spatial position flows up along a line like this that heads off to time like infinity, or the tip of the diamond up here. And so with time evolution, the endpoints of this region that I'm evaluating the entanglement entropy are being pulled up, well, in the geometry of the Penrose diagram, they're being pulled up closer and closer to one another. In the geometry, the real geometry, not the conformal geometry, they're actually a fixed distance away from the defect. So here's my boundary, or my bulk picture. What does a time slice look like? Well, again, one of these diamonds is covers half of the boundary. And here's the other one on the other side. I've got a horizon. This intersection runs across. One thing to note is that the 2 diamonds meet right where the horizon touches infinity. And that has the interesting effect that these blue regions here, it starts at some small step away from the defect and runs off to space like infinity, but there it actually meets the blue region on the thermal field double geometry over here. And so, in fact, I'm asking for the entanglement entropy of 2 regions on the boundary of the ADS space instead of 4. We can ask about this time evolution, and what you can see is that these dots, or the boundaries of my 2 blue regions, are being drawn closer and closer towards the brain from this perspective. Now, the point is that picture may be a familiar one from just standard calculations or discussions of holographic entanglement entropy. In particular, if we get rid of the brain, just think about ADS space, and we think about entanglement entropy of 2 regions on the boundary of ADS space, what we're familiar with is that they're typically 2 saddles that are competing to give the minimal RT surface. In particular, there's a disconnected saddle where the extremal surfaces just cap off each one of the regions separately. And then there's a connected phase where the extremal surfaces actually join the 2 boundary regions through the bulk. I've also shaded in the region inside the appropriate saddle to indicate the entanglement wedge. And one of the things I'll remind you about is entanglement wedge reconstruction, which says that using data in the boundary here, or in the boundary theory, I can reconstruct everything in the bulk inside the entanglement wedge. So in this region, in this context, it's not too surprising. Given data here and here, I can reconstruct what's going on in the bulk close to those 2 boundary regions. But the surprise then is in the connected phase, the boundary data doesn't just tell me about regions or the bulk regions near those 2 boundaries, but it also has information, or the boundary state also has information that tells me what's going on deep in the bulk or in the center of the ADS space. So having given you that reminder, all I'm going to do is I'm going to draw again a green line through the middle of those 2 pictures. And now we're doing black hole physics. And in particular, in what I'm saying is that at early times, one finds that this is the appropriate saddle. And so I have RT surfaces that are just close to either one of these 2 boundary regions. But one thing to note is that they stretch across the horizon, this dashed orange line. And so what one finds is that as time passes, the entanglement entropy actually grows. And so this is really the growth phase of that page curve. Now, and this is the more interesting phase where I've got the connected phase, or the RT surfaces now cut through, not the horizon, but they cut through the brain where the black hole is. And in this context, what one finds is, in fact, that the entanglement entropy is fixed in time. And because of entanglement wedge reconstruction, what we know is that the boundary state actually has information about what's going on in the interior here, namely on the brain. And so that is nothing, this part of the brain that's enclosed by the RT surfaces or by the entanglement wedge is nothing other than the quantum extremal island. And the boundaries of that, i.e. the places where the RT surface intersect the brain, are the quantum extremal surface. Now, and this, of course, is the page phase. Now, I seem to be running out of time. Can I have an extra, say, 5 minutes or so?
Yes, sure, of course.
Okay. So what I kind of cheated there, and I want to explain what's going on, because all I ever did was bulk entanglement entropy calculations. I just used the usual RT formula. And in this slide, you can forget about this term, but we're just using the usual RT prescription, but I'm talking about it as though, I have the island rule. I have an island. I have, this expression. And this is really this translation between the bulk perspective, the third of our descriptions of the system, and the brane perspective, where I have the boundary theory and the gravitating brane. And so I want to explain how I get from here to here. And so in the bulk, or in the RT formula, what I'm told is I'm supposed to extremize, I'm supposed to find the extremal surface in the bulk that's homologous to my boundary region. And so I'm assuming here that I'm in the connected phase. And so my RT surface will look something like this. But I'm actually going to do the extremization in 2 steps. The first thing I'm going to do is I'm going to extremize the RT surface away from the brane, away from the green line. So I'm going to satisfy some equation, some local equation about the extrinsic curvature down here in the bulk of the space-time. And so this is, I've just got half the picture. What I'm showing you here is that the solution here actually there are actually lots of solutions. And the difference is how they intersect the brane here. And the reason for that is, remember that, if I restored the rest of the geometry here, and I was doing some, a holographic entanglement entropy calculation, then what would fix what would completely fix the RT surface is data about the entangling region on the other surface out, or on the putative asymptotic boundary out here. Here, I'm not giving you that data, and so there's a lot of freedom in what form or where the brane can, or where the RT surface can end. And that's really what's giving us this freedom in the intersection. So there are lots of candidate extremal surfaces, and they all differ in how they intersect with the brane. Now we might think about, what are the contributions of these surfaces? Well, there's going to be a divergent contribution, a UV divergent contribution, where these surfaces reach out to the asymptotic boundary. And that has a well understood interpretation. There's the usual area law, and then there are higher order corrections. As I look further and further in the bulk, there are terms that are independent of the UV cutoff. And so there's what I'll call the finite infrared contribution. But then as I follow the surface further and further out, remember that this brane is near the putative boundary. The rho was very large. And so these contributions from the bulk area are getting very, very large here. And so they look like they're going to diverge, except that the brane acts like a finite cutoff. And if you look at those contributions, which are the analog of these in detail, and you compare with the details of the boundary theory, what you find is that you're finding those contributions are, in some sense, the gravitational entropy associated with the intersection of the RT surface with the brane. So it starts with a Bekenstein Hawking term. There's the area, just like there was an area over here. But now, rather than the cutoff to some power, what you have is the effective Newton's constant associated with the brane theory. And just like there are higher curvature corrections here, there are higher curvature corrections here, but they can again be interpreted in terms of the gravitational theory in the bulk. And in particular, these are, the curvature terms are like the wall terms that are associated with higher curvature gravity, but there are also some extrinsic curvature terms, which Dong suggested also appear in the gravitational entropy. And so there are these 3 contributions, but I can really split it into 2. I can think that there is a set of contributions that I can associate with the entropy of the quantum field theory, namely the boundary conformal field theory, living both here on the blue asymptotic region, but remember there's a boundary CFT that lives on the green region as well. And then there's a second contribution which corresponds to the gravitational entropy of this intersection surface. Now, I haven't finished extremizing my RT surface. The one thing that remains to be done is to vary over those intersections. Okay, so that's what I just said. The one thing that remains to be done is to vary over those possible intersections to really identify the extremal RT surface. And so what am I doing? And I do that, well, I'm varying over these boundary or these intersection surfaces. So I'm varying over the possible gravitational regions on the brain. Namely, I'm varying, or I'm extremizing over the possible islands from the brain perspective. And so that's then the translation of this bulk calculation to this island rule in the brain perspective. The first step, I extremize in the bulk away from the brain. That evaluates this quantity in the brackets, with the one caveat that I'm not just getting the Bekenstein-Hawking entropy. I'm actually, if I work hard enough, I get the Wald-Dong entropy, or I get higher curvature corrections contributions as well. When I finalize the extremization, what I'm doing is I'm varying over the islands. And so I'm doing this step here. There's also this minimize step, but that's like deciding, am I in the connected phase or the disconnected phase? I just assumed in my pictures that I'm in the connected phase. And so there's a precise translation then between what we do in evaluating this bulk formula and what our friends in Princeton postulated as the island rule. And that is giving us then, again, the entanglement entropy of these boundary regions. A quick comment, well, I've run over. A quick comment for the experts is that you can think of this, the entanglement entropy question, not in terms of the blue regions, but in terms of the black regions instead. You'll get exactly the same surfaces. Now I'm considering entanglement entropy of two regions on either side of the black hole horizon. This is very similar to something Hartman and Maldacena did. They saw very similar curves, but they explained it in a very different way. They didn't have brains, they didn't have black hole, or well, they had black holes, but the interpretation was different. There's this point about these intersection surfaces always being away from the horizon, i.e. the island extending beyond the black hole, and that has something to do with entanglement wedge nesting. I've really run over, all I'm showing you here is some calculations in higher dimensions. You can use this context to try and understand some of these questions. I'll let people ask me if they want me to come back to this. I should really just end and thank you for your attention and really say that there's still lots to explore in this game. So thank you very much.
Thank you, Rob, for a very nice talk.
Thank you.
So questions?
Well, let me try one, Rob. So in your picture with the artist surface hitting the brain, if you can show it again.
Let's see.
So this surface, whatever, yeah.
Where is it? There's this.
Yeah, there.
That?
So the surface goes through to the other side, right? Now, do you expect it to have no kink at the brain? And if so, doesn't this fix the angle at the brain?
No. Oh. Well, yeah, okay. You can understand the intersection here in terms of a boundary condition, and the boundary condition becomes even more fun if you include these intrinsic terms on the brain. But but the same would be true in that, well, the description that I talked about before would be more or less the same, in that you could find lots of surfaces in the bulk that satisfy vanishing trace extrinsic curvature, and then you'd look through that catalog of bulk surfaces and find which one satisfies the right boundary condition, because satisfying that boundary condition means that I really satisfy the true extremality. As a pragmatic statement, though, and there's a lot of discussion of those boundary conditions in one of the papers if you're interested in the details. But as a pragmatic statement, though, what you really do, many of these calculations are numerical, and what you really do is you look at the various surfaces and follow the procedure that I described, where the last step is, well, you actually vary the surface and see does the area go, or the intersection, and does the area go up or go down when I push the surface.
But I guess that's my question. I mean, in your other figure, you had many candidates.
Yeah.
And if you look at the whatever you had it,
picture like
here, and most of them would involve a kink at the brain.
Yeah.
So I was wondering if this is an admissible singularity in the RT rules.
So I guess the answer is no, that when you find the extremal surface, and I have an ordinary brain that just has a tension term, what you'll find is that the RT surface goes smoothly through the brain. If you add, it turns out, if you add an intrinsic, well, okay, so we can stop there. Or if you add an intrinsic gravity term on the brain, it turns out that actually induces a small kink. But again, when you find exactly that result when you ask what is the surface that actually extremizes or gives me the minimum area.
Okay, thanks. So in a sense, it's enough to ask that the angle here be a right angle, and then that's, if you don't add the Einstein term,
right?
Then that's basically
right.
The description.
Yep.
Great, thanks.
Rob, so can I just try my earlier question again? It's a more general question. And I don't mean to put you on the spot, because this is not a kind of thing that maybe you can answer in a few minutes, but maybe it could open the chance for a discussion separately. Mm-hmm. So I've actually read through a fair number of these papers, and I seem to find that they are going in the following loop. So let me state my difficulty, and I'll let you say whatever you'd like to. The black hole case is different in a basic way, in the sense the quanta have left and gone far away to asymptotically flat space, where we have.
Can I just interrupt? When you say the black hole case, you mean the evaporating black hole, or
yes?
Or
yes.
Yeah, okay.
Evaporating black hole, yeah, not this thing that you talked about.
Yeah.
So then, once the quanta are in flat space, there is a well-defined notion of holding a quantum in your hand and checking if it is in a pure state or entangled state. With many similarly prepared states, you pass them through a Stern-Gerlach and you get a definite answer. So what I find is that in the end, all that one has found with this Almeri multilateral paper and so on is that, not unsurprisingly, if you just take 2D gravity, you do not get the information out. The page curve does not turn over. The quanta which are in the island are exactly the same quanta. What is being called the island is exactly what we used to call the interior part of the Cauchy slice. They're exactly entangled the same way that CGHS found them. And then they have simply changed the definition of what they want to call radiation to include the quanta inside, so that by definition now this whole thing is not entangled with anything. But if you take this to be a new definition of what you want to call the radiation, or the entanglement of the radiation quanta, you would simply be wrong. And it would be wrong in the sense that if you take a radiation quantum and pass it through a Stern-Gerlach, it would not do what you expect a normal pure quantum to do. So you have tried to make a new definition while not changing the underlying physics. So in a sense, you haven't done anything apart from where CGHS was, which meant information hasn't come out. You made a new definition, but the definition is clearly wrong because it doesn't tally with what a pure quantum should be doing outside. So I know this looks very blunt, but this is what I found after looking at all these papers. I'll let you give me your reaction.
So what I'll say is that you should be able to make all those same complaints about the equilibrium situation as well. And so what I have here is the advantage of what I'll call a bigger theory. I mean a UV theory. I have the bulk description. I mean, that's really what I'm playing with. And by these standard rules of ADS-CFT, I know that, the information, there's a bunch of excitations in this blue region and this blue region here. But I know, again, by standard rules or standard lore, that those excitations, which are standard quantum field theory excitations, somehow encode information about this region of the space-time, i.e., if there are excitation, if I added some extra excitation on the brain and it fell inside the brain, I would be able to see that somehow with that would modify the boundary state here in some subtle way that I could, decode that excitation falling into the brain, the brain black hole. And I think it really comes down to, what the heck is this island rule really about? I mean, it's I'm not sure if I like this and I'm using this as an excuse to say these words anyway. There's a distinction between this side and this side. This side, I'm working in this what I'll call semi-classical description, and I'm doing various calculations. But what this formula says is, well, you don't have a full, complete description here, but you'd better do the calculation this way if you want to understand what the correct or the entanglement entropy that I have in the full theory is. And so, what that's saying here about one of the things I did not emphasize, and I apologize for that, is that here I said that I have 3 descriptions of the system that I'm interested in. I basically ignored that and I worked mostly down here in the bulk, but then I gave you an interpretation in terms of this brain perspective that's sort of the halfway house. But what I have to emphasize is that these 3 pictures really aren't all on the same footing. These are what I'll call, a UV complete framework. When I'm talking about the system here, I'm really just using standard rules. I'm just using ADS-CFT, and I know this and this are equal. That is what the ADS-CFT means. And when I calculate the entanglement entropy using holographic entanglement entropy, I'm really calculating in this context here. And so that's what they call, the Princeton paper called the full quantum description of the radiation. When I go to this picture here, I know that that is not on the same footing. That theory, that's an effective description. And Randall-Sundrum actually emphasized that, and I hinted at it before perhaps, in that I have a theory with a cutoff, and I know that if I look at quanta that have energies beyond that cutoff, well, this description just breaks down, and I'd better go back to thinking about it in terms of the bulk theory. And there's also some subtleties about the coupling between the 2 systems. But it's when I translated the discussion to this perspective that I talked about, the gravitational contribution and the quantum field theory contribution. And so what I was doing is I was trying to translate the my UV or my RT prescription, which is just a standard prescription, down into, a language or a set of calculations that I can do in the brain perspective, that will reproduce this answer that I know is the correct answer from my UV theory or from my bulk perspective. And what we saw, or what I argued, is that, yeah, in fact, the island rule does give me the answer that I expected, or that I went the wrong way. But what this says is that the island rule is just a mnemonic. It's just a rule that says, well, if you don't have the complete UV theory, if you just have some effective theory, some low energy theory, and you want to evaluate the entanglement entropy, well, the correct answer in the full quantum gravity theory is going to be given by a calculation that looks something like this. It's not going to be given by our standard quantum field theory calculation. And we saw RT told us that, there's a phase transition, an island appears, yada, yada. But it's really just a mnemonic. And in this framework, you're never really going to be able to see, those hidden correlations that I talked about. And one of the questions you might ask is, well, this is an answer that gives me the page curve, but did the UV theory really dictate that was going to be the right calculation? I gave you an example, namely holography, where sure enough, this is the right calculation. But for example, I think you mentioned CGHS or RST gravity, Strominger, Hartman, and I've forgotten the unnamed grad students, I apologize. That's an example of 2D gravity where they argued that, well, this is not the right calculation, and that's a theory, in fact, of remnants, and you don't restore unitarity in the Hawking radiation by itself. And so it's something that these folks pointed out. It's a real question. We now have a prescription for restoring unitarity, but how do we know that the UV theory really chooses this as the right answer? And I gave you an example where I hope I argued that this is the right answer in the context of my holographic setup, but it need not always be. And if all I have is the effective gravitational theory, that will always be really a question mark in the calculation.
So actually, could I follow up on that?
Sure.
I'm glad you mentioned what you just said, because that's exactly, I think, the place where a lot of what is being said is not correct. So somehow the words being said around this so-called, recent developments is that, well, there is some very quantum complicated theory we don't know anything about. But if you look at an effective semi-classical theory, well, here is a rule which is good for the semi-classical purpose, and it actually gives you the correct answer in the full quantum gravity theory. And that is simply wrong for the following reason, in my opinion. Let me just give you the reason. When you go near infinity, there is no two ways on what is semi-classical or exactly quantum, because semi-classical has to agree with quantum. We can talk about again if that's a concern. The fact that what these people were trying to do, what the Maldacir Almeida paper were trying to do, their goal is to argue that you can maintain a semi-classical description where, to leading order for the production of a few entangled pairs, the horizon looks like a smooth place. If the horizon doesn't look like a smooth place, like a piece of coal, there's nothing to ask. On the black hole side, you can do the fuzzball. The problem is already solved. If you have a normal piece of coal, there's no puzzle. Now, they are trying to actually say you have a smooth horizon, at least for the purpose of emitting a few pairs, so that geometry means something. And because some subtle things happening here or there, the page curve comes down. But in fact, we know that's not possible, because the small correction theorem tells you it's not true. And then when you go back and see where those calculations, those arguments break down, different models with different papers. If I look at the Marolf et al. Papers, the evolution in the interior is actually not unitary. You can see which states are actually going from finite norm to zero norm. if you look at the papers which have some words from Maldacena, there are non-local effects which actually connect you from inside to outside. If you're going to pick up a particle inside and put it outside, of course, then there is no puzzle. But if you simply say that you have a description which looks to leading order semi-classical around the horizon, and in some delicate way, there's some more exact problem which somehow makes the page curve comes down, and there are no non-local effects, that's actually proved to be not true by the small correction theorem. So this is what I would like to go through in some maybe more detail. I don't want to pin you down here because obviously we can't do it like this, but maybe we can have a longer discussion. We can see there is actually no out here. The reason you are getting away with whatever you're saying with this closed area here is that if you're saying within the ADS-CFT domain, because everything is localized in that region, there is no independent asymptotic way where you can define what you mean by the entropy of something. So you can move some amount of the entropy from one degree of freedom to another. You can change the cutoff. You can put something here and there. But in the case of black hole, it's very clear. You take a black hole, you emit quanta. Now the quanta are like ordinary particles in the lab. You hold them in your hand, pass them through a Stirner-like and ask, are they pure? And there the small correction theorem tells you, you actually can't do what these people are claiming they're doing. You either have to violate unitarity in the interior explicitly, which I can show you where it is in the Merrill-Maxwell papers, or you're going to get non-local effects, which I can tell you what they should be. But you simply can't have your cake and eat it too. So that's why I don't follow what the whole goal of this whole enterprise has been.
No. Well, I think we both recognize this in the beginning of a discussion. I mean, I think all of your complaints should apply here. So it'd be interesting to understand in more detail. I claim this is a system which reproduces a lot of the physics that's been talked about in other models and other papers, and it's all just standard ADS-CFT that we all are familiar with. The only thing in listening to you that comes to mind is you mentioned non-local, and in some sense, there is perhaps a non-locality here, in that, in the brain prescription, all I talk about is the boundary theory, the black and blue, and something on the green. But at some level, I know that, what I really mean, or the real physics, quote unquote, the better description of the physics is this bulk, or this full, or this is a cartoon of the full picture. But I mentioned this as a subtlety about the coupling, but here I can see that in some sense, if I want to get here from here, well, in the brain perspective, the only thing I can do is I have to go up and around. But I know in the bulk physics that, somehow I can just wander straight across from here to here. And so maybe that is a extra bit of physics, some non-local physics, that somehow, well, I don't know, it's something that's not acknowledged in the usual discussion of whatever, these islands and whatnot. And so maybe that's something towards making, resolving the tension that you're pointing to. I don't know, but it's the beginning of a discussion.
No, absolutely. I think what you just said is exactly what I would say as well. All that they have done is said that, yes, you get the normal remnants. If there's non-local physics, which can pull me from inside the remnant all the way to infinity, not non-local across the horizon length, but across the, all the distance to where the Hawking radiation is. If I have non-local interactions over that distance, my information can come out. And I agree that is true. I also think it is wrong. But if somebody says I can put a particle from here and non-locally put it somewhere else, that can obviously get the information out. And that's all that has been said here. All these papers have simply come to this conclusion that you have not got the information out, and some hitherto unknown effect can pick up the quanta from inside and put it outside. And yeah, absolutely. Let's just find some other time and chat about this in detail, because indeed, I've been reading some of these papers, and I'd love to go over them with you.
Okay,
Maybe we
sure.
can, so there's been a lot of questions. I suggest that we stop the recording. We thank Rob once again. So thanks a lot, Rob, for the very nice talk and the
Thanks.
detailed